morning, everyone, and welcome once again to AP Calculus BC Live. With this, our 26th episode that's going to cover algebraic stems connecting AB with BC. We didn't get a chance yesterday to celebrate our 25th episode. That was our sort of a silver jubilee, but we have been together for a long time. I think it was since the last week of March that Brian and I have been coming at you every weekday. Hopefully, we've provided you with a little bit of help, a little bit of security, a little bit of confidence in your preparation for the AP exam. And it seems like we've been together for so long that, I don't know, I feel like we're sort of becoming maybe friends, right? Or maybe even better yet, maybe family. Maybe it's like we're Uncle Brian and Uncle Tony now. And I'm not talking about the creepy uncle who kind of shows up for Thanksgiving dinner, eats the turkey, and then just kind of crashes on the lazy boy the rest of the day. We're talking about those really cool uncles who will help you with your math homework, who will maybe take you to ball games, take you to rock concerts. Maybe that's who we are. And whatever the case, we are happy to be with you today with our algebraic stems lesson with connecting AB with BC. As always, you can grab the documents off of the Dropbox that's located in the link to the video. And I am so happy to be with the greatest partner that I could possibly be paired up with, and that is the incomparable Brian Passmore. Brian, how are you today?
Tony, I'm doing pretty well. Right before we came on the air, by the way, our producer, people at home don't know this, that, we just show up on the air. We're the on-air talent, right? So we're kind of divas. We don't have to prepare much besides our problems, but we have a College Board person behind the scenes, Sarah, who's an amazing producer, and she gets things ready for us and notified us yesterday. We didn't know this, but our screens were flipped yesterday. Did you realize that? And so when we gave a high five, apparently we were going in the opposite direction. So that pretty much sums up my technology in a nutshell. But other than that, I'm scrambling a little bit today because I didn't really get up in time, right? These are early. I feel bad. I mean, it makes me even more impressed for our friends on the West Coast that are getting up at 6 a.m. Shout out to all of you guys and girls, but I didn't have much time this morning to get things ready. So I'm trying to eat breakfast while we're getting here and scrambling at the last minute. So I'm hoping I'm not going to be sort of out of control this morning.
Well, Brian, just to be completely on the opposite end of that, I got up about an hour and a half earlier than normal just to kind of run through our problems again, try to see if I can find alternative solutions. So I've been at this for a while already.
And I think that really, Tony, illustrates the difference between you and I. You are the most meticulous, like plotting planner person I know. And people who are watching, it's obvious because even when you do your handwriting, I always call it the Tony record font. I feel like in my Word documents, I go through all my fonts, Courier and Times New Roman, that there should be like under T's, the Tony record font, because you write so perfectly. And I think everything that you do, like we spent time last night doing these problems and yesterday, and I know that you knew exactly what you were doing because we left it last night, but yet you still had to get up and plan. And for people at home, a quick story about Tony. I want to reinforce just how meticulous and planning and careful he is. We drive to Kansas City each summer together with another friend of ours named Lee, and we go there. That's where the calculus exams are read. That's where we read your free response exams on a typical year, not this year, but so we all carpool because Tony and I are friends in real life, and each year we kind of rotate which one of our three friends drives. And Tony drove the first year, and we banned him from driving because he drives so cautiously. It made a 7-hour trip like a 9-hour trip. So like, nope, no more, Tony, you can't drive. But the first year he drove, we were like 5 miles away. We were just outside of where we were going in downtown Kansas City, and traffic came to a halt. I don't know if it was just rush hour traffic or an accident or something. But we're sitting there and you're like panicking, Tony. You're like, guys, I should just get off right here and get gas. What do you think? We need to get gas. I want out of gas. And we look down and you have like a half a tank of gas in your gas tank, and you're worried about, we've got 5 miles left. Like that's you. Like you're the cautious planning, always tank full guy.
Half a tank. That's such an exaggeration. It was way below a quarter, and it's. I kept telling you it's a related rates problem. You of all people should know that. As the gas in your tank depletes more and more, the rate at which the gas depletes more, it's increasing. I mean, everybody knows that, right? I was a little scared. And don't get me started about this whole problem writing idea. A lot of times we'll have these things finalized about 10, 11, maybe midnight, even sometimes after. I'm like, okay, Brian, I think we're good. I'm going to go ahead and go to bed. And then you stay up and you get these brainstorming ideas, and then all the problems are different in the morning. And I'm like, what are these? So yeah, don't and don't get me started also on when you and I are kind of working together and we're driving to do workshops. It's happened in California, it's happened in Chicago. I'll say, Brian, you go and navigate more than once, not just once, but more than once. You've taken us to the wrong school.
That was part of the circle of trust, Tony. We promised we were never going to tell that story. That maybe on more than one occasion, I forgot to plan, look up where we were going. You'd ask me, "Hey, the night before, did you look up the map?" I got it. I got it. Tony, you stop worrying. You were fine. And then the next morning, a half an hour later, you're like, I don't think we're going in the right direction. And I'm like, oh yeah, I forgot. We went the wrong direction. So, okay, maybe we're like fire and ice. So it probably is good that we're partnered up.
That's probably right. Yin and yang. I agree. Lennon McCartney, whatever we want to call it, I agree with that. And speaking of great partners, I'm going to turn this off to you so that you can get us going with our first free response questions of the day.
Perfect. So let's just jump into it, you guys. This is going to be our BC1, and our stems today are algebraic stems. So all the problems that we see, we're not going to have any graphs. We're not going to have any tables, just pure algebra stems. It's a little bit trickier this year because since we're at home, we're not going to have the same type of algebra problems that we would have in a typical year. Usually with the algebra questions, it's a lot of manipulation, but on a typical exam, a lot of that could have been done if you have a CAS calculator or a Google or a math app or Wolfram Alpha or something you could look things up with. So they might have to be a little bit more creative in how they write questions to prevent some of that if we're going to use some algebra stems. So this would be a really good example, I think, today of some types of problems that maybe could appear that you might be eligible for under this new format, right? So our first problem, we have this nice stem of g of x equals f of x over the quantity 2x times 2x minus 1. And then we're going to do some different things with that stem. So we're going to see that g of x function change throughout this problem. So part A says, if the slope of the line tangent to the graph of g at x equals 1/4 is negative 12, find the slope of the line tangent to the graph of f at x equals 1/4. So there's a lot of information there. And as we're getting closer and closer to the exam this week and even next week, we want to give you more opportunities to, instead of just listening to us walk through problems, give you that first chance of reading a question, internalizing it, and thinking, okay, how would I start this problem? Because for the most part, we've kind of just given you that first step. Here's how we're going to solve this. Well, you're not going to have that nudging for Tony and I during the actual exam. So it's going to be really important that you see these kind of problems and think through, what would I do on a test if I'm staring at this, blank problem and I'm all there by myself? How am I going to handle this? And I listened to a webinar last night by Trevor Packer from the College Board, where he was talking about these exams. And one of the things they're sharing with students and teachers is that on this year's test, they're going to write questions where you can't just Google facts and answers. They're going to ask you things that you know, but in ways that you haven't seen possibly, or make you apply it to new situations to see if you really understand these concepts. And I think part A is a good example of that. So think about, if you had this question, how you might tackle it, right? The slope of the line tangent to the graph of g, so I know they mentioned g at 1/4 is negative 12. Find the slope of the line tangent to the graph of f at x equals negative, or at positive 1/4. What might be a good strategy? Well, I'm thinking, if I'm tackling this problem, I don't really know where it's going to take me or exactly how to solve it, even as an experienced calculus teacher. But what might be a good strategy is just start kind of jotting down what you know. Can we start interpreting these words into mathematical equations or ideas? And so it tells me the slope of the line tangent to the graph of g, right? Well, what does that mean? Well, we know there's a connection between derivatives and slope of tangent lines, right? So it tells me the slope of the line tangent to g at 1/4 is negative 12. If I just interpret that, that would mean that g prime of 1/4 needs to equal negative 12, right? I'm just making that connection. And then I'm also told to find, so the question becomes the slope of the line tangent to f, right? So same idea, I want to find f's derivative at 1/4. That's the real question, right? But the first step is sort of taking the information they give you, especially if it's in words, and try to come up with some kind of equation or diagram or picture that might represent it. Because once you write that down, then it might help you decide, okay, now from what they've given me in the problem, this initial information, how might I be able to utilize that to solve this problem, right? But I think a big mistake we make is we just start trying to solve problems. We start doing stuff, right? Without thinking first about a plan. And a 45-minute test, there might even be a bigger, like incentive or a bigger lure for you to do that. Like, I don't have time, I have to just start solving problems. But sometimes you get into this bad corner when you do that because you haven't spent the 15 or 20 or 30 seconds thinking about the problem before you enter it. And if you do that up front, I think you're going to save a lot more time on the back end, because now I think you're going to feel more confident about where you're going with your work. And so we're told G prime and we're asked to find F prime. So we know if we're going to solve this problem, we're going to have a derivative somewhere, right? You can't find F prime unless F prime appears in your answer somewhere, right? So how am I going to get F prime to appear in a problem given an equation? Well, probably going to take the derivative. I'm hoping if I take the derivative of this G prime will sort of work out as well. So that's what we're going to do, right? So I wrote some information down, thought about, what that might lead to, and now we can go to the next phase, which is let's perform that first calculus step. In this case, let's differentiate both sides. So G obviously becomes G prime of X. And don't forget, when you have an equation, keep that equation. A lot of times we take derivatives and we just look at the right-hand side and we kind of ignore the equation, but the equation is still there. So it's going to be G prime equals, right? That's an important piece. On this right-hand side now, to take this derivative, we're going to have to use the quotient rule. We've got a fraction. To make it a little bit easier on us, I think in this problem, it might be better to go ahead and distribute out the denominator. That way we don't have this embedded sort of product rule, chain rule in the denominator of a quotient rule problem. So if I distribute this, we get 4x squared minus 2x. And so then the quotient rule, low D high, so it's going to be 4x squared minus 2x times f prime of x. Hey, there's that f prime that showed up. That's pretty good news. Minus high D low. So it's going to be f of x times 8x minus 2 all over the bottom squared, right? The 4x squared minus 2x quantity squared. So we've now taken the derivative. And once we do that, we realize, okay, we actually have some information. We know that x is going to be 1/4. If I plug in 1/4 for the x's, I also know that g prime will become -12, right? So let's go ahead and plug in what we know. So now we have -12 on the left. And then if x is 1/4, so today, I'm going to accelerate some of the algebra or the arithmetic, because I know that you're going to have a calculator with you on the exam. And so kind of doing that process is going to be a little bit easier this year because you don't have to do all that on the side on your own. So I'm going to trust that you could type these things in. If we type in 1/4 here for this x, you're going to get 4 times 1/4 squared minus 2 times 1/4. If you work all that out, it just is going to become -1/4, right? If you plug in 1/4. Then we're going to have f prime of 1/4 minus f of 1/4. Well, I don't know what that is. That can be a problem. How am I going to deal with that? But if I plug in 1/4 here for x, 8 times 1/4 is 2, and then 2 minus 2 is going to end up becoming 0. On the bottom, we have the same quantity as we had up here, so we're going to have that -1/4 quantity squared. So I have this equation. I have 2 unknowns, right? We're trying to find f prime of 1/4. This is what we're trying to get right here, which would be fine if I didn't have something else. But luckily for us in this problem, just by kind of trusting the process, 2 minus 2 is 0, and then 0 times f of 1/4, that's going to just kind of cancel out, right? It's going to become 0. So really all we're going to have is this -12 equals -1/4 f prime of 1/4 over -1/4 quantity squared becomes 1/16. And if I wanted to simplify this problem a little bit, I can just multiply the top and the bottom of this fraction here by 16 to get rid of this complex fraction, and we get -4 f prime of 1/4. And then dividing both sides by -4, lo and behold, we get f prime of 1/4 equals 3, and that answers the question. So instead of just telling us, right, hey, if g prime of 1/4 is -12, find f prime of 1/4. They could have just put it like that, but they put it in words instead and make sure we made those connections, right? So the answer to that problem would just be 3. So looking at part B, same function, but now we said, okay, look, if f of x equals 1, so this is going to be 1 in the problem, then this fraction using partial fraction decomposition could be written like this: 1 over 2x minus 1 minus 1 over 2x. So in this situation, when f of x equals 1, determine if the series of a sub n converges or diverges, where a sub n is just going to be g, right? So our a sub n is going to be this. So really, what we have here is just going to be the series of 1 over 2n minus 1 over 1 over 2n. Now, I don't know about you, but that's not really a series that I'm that familiar with, right? There's a lot of things that we could do with this. We could try to combine them into one or whatever. But whenever I have a series, we call this enclosed form. We don't have all the terms written out. It's kind of like the formula for the series. I think a really good first step when you're not sure what's happening here is just start plugging in some values for n to see what this actually looks like with values, right? Once you see the numbers, sometimes that gives you a little bit more information about what you're dealing with. So let's just plug in some values and see what we get. So if I plug in 1 for n, right, we're going to get 1 over 2 minus 1. It's just going to be 1 over 1. And then plug in 1 here as well. That becomes 1 minus a half. Now let's plug in 2 for n. If I plug in 2 for n, 2 times 2 is 4, minus 1 is 3, right? That's going to become a plus 1 over 3, minus plug in 2 for n, the second part, that's minus a fourth. If I plug in 3 for n, we're going to get 1/5 minus a sixth. And do you see the pattern, what's happening here? Once I plugged in some terms, it became a little bit more obvious what we have. So I don't even need to combine these terms. I just get this long series, 1 minus a half plus a third minus a fourth plus a fifth. And do you recognize what that series is? That's just the alternating harmonic series, isn't it? All right, this is the alternating harmonic series. And so this is the alternating harmonic series, which converges, right? We know the alternating harmonic series converges. The harmonic series diverges, but the alternating form converges. Now, we also could have used the alternating series test, right? If we wanted to, we could have said the limit of these terms approach 0, which they clearly do, the absolute values of them, and each term without the negative signs are decreasing, right? So we have a decreasing series and the terms approach 0. Those would be our two conditions to invoke the alternating series test. But in this case, it happens to be the unique series of the alternating harmonic series. So once we identify that, we could just claim that the series converges because it's the alternating harmonic series. So Tony, you're going to take us through a couple more parts of this problem, and then we're going to see another kind of cool FRQ the second half of the lesson.
Certainly, and we are going to take a look at that same function, that same g of x that Brian discussed here in part C and beyond. And again, we'll kind of think of that denominator as being multiplied through as 4x squared minus 2x under the f of x. Now, part C reads, if the function g has a critical point at x equal 1, find the x-intercept of the line tangent to f of x at x equal 1. And I think I may have forgot the word of there, find the x-intercept of the line tangent to f of x. Now, what we're going to do here is think about what is the definition of a critical point. Well, the critical point is a concept that's tied to the derivative. So we certainly are interested in taking the derivative of g. And if you recall, the derivative of g was done very well in part A. Brian took you through that process. So we're going to just borrow that answer. Once you've worked that out, it's your own work. It's yours to use. And so we have that g prime. And then moreover, for this critical point to exist at x equal 1, what that could very likely mean is that this derivative evaluated at 1 is going to equal 0. So if we replace all of these x's that we see in this pretty long derivative expression with 1, we would have f prime of 1, of course, and then evaluating 4x squared minus 2x at 1 would give us 2. And then we subtract our f of 1, and then evaluating 8x minus 2 at x equal 1 is 6. And then our denominator would be that 2 squared, which I'm just going to immediately call 4. And as I said before, one of the ways that a critical number can exist is for that derivative to equal 0. Now, because we have a fraction for this g prime of 1 value, the only way that a fraction can really equal 0 is if the numerator is equal to 0, or we could just multiply this 4 over and lose it. So if we look at a slightly different way to write that numerator, just plopping those coefficients out in front, we're looking at this equation, this relationship, which is where things start to get a little scary. Because of this elusive f of x that just permeates throughout this problem, we don't have that sense of security in being able to use a specific function for that. But if we could do that, then we could rely on a CAS calculator to do practically this whole problem. So what we would have to do with this is think, okay, well, one of the ingredients of finding a tangent line would be finding its slope. So let's go ahead and stay the course and find out what is the slope of this line f of x, which of this tangent line f of x, which means that we're going to figure out what f prime is at that value of 1. So if we solve this for f prime of 1, we could first of all add 6 f of 1 over to the other side, and then of course divide by 2. And then we come up with just kind of an interesting relationship, if nothing else. F prime of 1 is 3 times f of 1. It's sort of a relationship between the slope and the y value, but not a very specific numerical quantity. Now think about what are the ingredients to write the equation of any line? Well, we need, of course, a point, and we also need a slope. Well, we're doing pretty good in both of those departments because we have determined that the point would occur when x is 1, and then the y, well, there's really no other way to describe it than say f of 1. The slope we've determined to be just this symbolic value f prime of 1. I think we're going to be okay. I think that we can, or I'm sorry, 3 times f prime, 3 times f of 1. Let me get the slope right. The slope is f prime of 1, but I want the value over here on the right side, right? This is really what I'd like to use for that specific slope. Now we just stay the course and we write the equation of the tangent line. So a normal lines equation would just be point slope formula, y minus the y value equals our slope, 3f of 1 again, multiplied by x minus the x value. Now we have to think about, well, what is the question really asking? Did it want the equation of the tangent line? It wants the x-intercept of the line tangent to f of x at x equal 1. So in other words, we want to know where this line crosses the x-axis. And the x-intercept is just sort of another way of thinking that the y value is 0. It implies that the y value would be equal to 0. So if we go back to this equation and let this y be 0, we find this relationship to be true. Replace the y with 0. And then this x value at which that occurs can now be solved for. It's a very cool problem. If we divide both sides by 3 f of 1, you can see what's going to happen here algebraically, right? You end up with negative 1/3 on the left side, and then just simply an expression of x on the right side that you can simply solve for by adding 1 over, and x equal 2/3 is where that x-intercept is. So a very neat conceptual problem that really won't allow you to rely on a Google search, a photo math process, or a CAS calculator. Very well written problem. Brian did a great job with that one. Now, if we take a look at part D, we're going to move into a little bit of, I guess, BC realm here, and we're going to consider the series A sub n and the series B sub n as n goes from 1 to infinity. And we're going to define A sub n as f of n, B sub n as g of n. And then we're going to give you the fact that the limit as n approaches infinity of the absolute value of b sub n plus 1 over b sub n is 11/7. So we're going to use the ratio test to determine if this brand new series, the summation of 2/3 to the nth power times a sub n, converges or diverges. So we sort of got a 3-ring circus going on here, a lot of things happening. So let's just kind of digest it a piece at a time. So what I'm going to do first of all is I want to get a better handle on this new series that they've provided. So let's go ahead and rewrite this summation 1 to infinity of 2/3 to the nth power times a sub n, but I know that a sub n is just this f of n, and if I just slightly manipulate this equation up here and solve it for f of x, I would have f of x equal to g of x times 2x minus 1. All I'm going to do now is just replace those x's with n's to get this looking a little bit more like a series of n, and I have something along the lines of this. Once again, it's written very generally, right? This g of n is sort of what's keeping us honest. We don't know exactly what that is. So we are going to go ahead and use our ratio test with this fairly interesting nth term expression now. So we're going to take the limit as n approaches infinity of the absolute value of, and then I'll think about this as being split apart. So I have 2 to the n power. Now, if you remember the ratio test, you would just change all of the n's to n plus 1. So we're going about our business doing that. And I'm going to go ahead and simplify. 2 times the quantity n plus 1 would be 2n plus 2. 2 times the quantity n plus 1 minus 1 would be 2n plus 2 minus 1, or 2n plus 1. And then I've got the denominator here of 3 to the n plus 1. And then instead of dividing that by the nth term expression, I'll just multiply it by the reciprocal. And what that would mean is I would have a 3 to the n up in the numerator, and all of that would be placed over 2 to the n, and then the rest of what I had originally up in this expression, g of n times 2n times 2n minus 1. Now, that looks like a lot, but you're going to be surprised at how really quickly and easily it simplifies. So if I take this limit as n approaches infinity and start doing as much simplifying as I can, I notice that, oh, well, this 2 to the n plus 1 over 2 to the n, that's just going to be a 2. And I'll do the same thing with this 3 to the n over 3n plus 1. That's going to be a 3 in the denominator. And then I'll start to look at, oh, let's take a look at the g values, the g function values, which unfortunately I can't really do much of anything with. I have g of n plus 1 and g of n on the top and the bottom respectively. Can't do much there. And then furthermore, there's not a whole lot that I can do, unfortunately, with these expressions of n. 2n plus 2 times 2n plus 1 all over 2n times 2n minus 1. Well, that seems to put us in a bit of a predicament, but all is not lost, because there are some things that now are about to happen. And if I kind of think about each of these as being 3 separate limits separated by a multiplication, I won't write that out, but we'll talk about how we'll simplify those. As the limit of the 2/3 is just the limit of a constant, which is a constant. Now, it's this next piece that's quite interesting. This g sub n plus 1 over g of n plus 1 over g of n is really nothing more than utilizing the idea that this limit up here is true. Because remember that g of n is the same as b sub n, if we think of it more as the nth term of a series. So we can then apply our limit to this expression and use that value that we're told that that's equivalent to, 11/7. And then as far as the limit of this last expression is concerned, if we think about what the leading coefficient of the highest degree term is on the top and the bottom, we end up with essentially a 4n squared on the numerator, a 4n squared on the denominator side, and that limit, of course, is just going to be 1. And of course, the absolute values really don't play a big role because everything is nice and positive. And once all of this is simplified, we get 22 on top, 21 on bottom, which is oh so close to that value of 1 that we have to compare this to. Unfortunately, this one is greater than 1, which means by virtue of the ratio test, our series will diverge. Remember, for the ratio test, if your limit is greater than 1, your series diverges. If it's less than 1, your series converges. If it's equal to 1, you need to use a new test because the ratio test is going to be inconclusive. All right, let's go ahead and wrap this up really quickly with our part E here. And our part E gives us an integration of g of x defined as 1/2 natural log of 2x times 2x minus 1 in absolute values plus c. Our job is to find an expression for f of x. Now, to start the wheels turning on this problem, I'm going to say, let's define capital G. Let's let capital G be this expression, 1/2 times the limit, or the natural log, sorry, of the absolute value of 2x times 2x minus 1, all plus c. Now, the reason why I defined that as G is just so I could show some notation and think through this process that, well, if I were to kind of think about this integration of little g of x, then by golly, I might want to consider taking the derivative of this expression. Take the derivative of capital G of x, which we know is going to be equivalent to the lowercase g of x, right? That's the relationship that exists between derivatives and antiderivatives. And this derivative of capital G is, you could do this a couple of different ways. I think maybe the easiest way is to think about these two logarithms being separated by a plus sign and taking the two individual derivatives of those logarithms so that that 1/2 comes out in front. The derivative of natural log of 2x, well, that would be 2 over 2x, which reduces to 1 over x. Then we can drop our plus sign down. And then we have the derivative of the natural log of 2x minus 1, which is another u prime over u, or 2 over 2x minus 1, if you want to call it that. And then the derivative of c is 0. I'm not going to put the absolute values in because we understand that the domains are going to change a little bit. We've kind of acknowledged that there is a restriction originally. So now, what do we do with this? Well, that's a great question. We know that g of x is equivalent to, well, the guy that we see in the original stem of the problem, f of x over 2x quantity 2x minus 1. Now what this allows us to do is isolate in on this f of x that they want us to find, which really can be accomplished by just multiplying over this 2x minus 1 expression. So we have 1/2 times the quantity 1 over x plus 2 over 2x minus 1 times 2x quantity 2x minus 1. And that would be your f of x that we talked about. I'm not going to talk about simplifying this because that's really the last thing that you need to worry about, not just on this year's AP exam, but really on any AP exam. However, if you're interested, this actually does simplify really nicely, and you can practice this later just for your own amusement. It turns into just simply 4x minus 1. So Brian, I think that wraps up our BC1 question. I'm going to let you take BC2, and we'll try to get through as many parts of that as we can this morning.
Sure, absolutely. So we're going to take a look at one more of these free response problems. And Tony, I just sent you a message that we might skip part C. That way, we might get back to you a little bit sooner. So I wanted to make sure you're ready for that. We kind of have a plan each day. I'll do these problems, you do these problems. And if timing is not working out, we might skip a piece. And so I want to make sure Tony knows I'm planning ahead, Tony, right? I'm trying to be a planner like you are. So I don't just do it on the fly, right? But so BC2, we have a new function now. And now we have a piecewise function. So I think both of these examples are really good possibilities of the kind of things that you might see on the exam, where the first problem was a kind of normal equation, but in that equation, we had that little f of x on top that was not quite defined. And so it created some abstractness and it created some flexibility how the problem can take some different twists and turns. Another good example is a piecewise function. We can do a lot with piecewise functions. And notice again, we sort of have a generic function ax plus b for part of it, because then we're able to solve some problems and change those a's and b's out from different parts and kind of create some flexibility. So part A says, hey, find the values of a and b. So instead of giving you a and b, find the values of a and b such that this piecewise function is differentiable at x equals 0. We've done a lot of continuity problems, right? How do you know something is continuous? And we're getting better at showing continuity, find the limit from the left and the limit from the right and show they're the same, show there's a point on the graph, show that all those answers are the same answer, and thus we have continuity. We haven't done a problem with differentiability. So how might we tackle a question like this? Well, if we're talking about something being differentiable, especially a piecewise function, we're talking about its derivative, right? And so I think it's important that students realize with piecewise functions, we can do all the same calculus that we do with normal functions. It just has two pieces, right? And I know my own students, when they come into calculus, don't usually feel as confident with piecewise functions because they just don't do a lot of them in the courses leading up to my course. Or maybe they did some in Algebra 1, a little bit in Algebra 2, maybe even revisit it in pre-calc, but never had a whole lot of experience with it. So they feel a little bit, uncomfortable with the notation and how things work. But really, it's just two functions in one. It's pretty simple. So if this is our function of f, we can certainly write an equation for f prime. So I think that's always a good start. And I would do that because I want to know if f is differentiable. That means that f prime of 0 has to exist, right? If something is differentiable somewhere, it has to have a derivative there. So it would help probably to have an equation for f prime. And so in this case, ax plus b's derivative, right? Well, a is a number. So a number times x, the derivative is just going to be a. That b is going to go away, right? If no matter what number it is, 1, 2, -7, it's going to always go away if you take the derivative. And that's going to work for x is less than 0. Then our bottom piece is that exponential function. And if we take this derivative, we're going to have to do the chain rule, right? So we leave it the same, then multiply by the derivative of the exponent. And we're going to end up with -8e to the -2x. And the idea here is when you do a piecewise function, I know the original problem had an equal sign, meaning this function could use 0 here, right? But when you take a derivative, we don't always know if those two pieces are going to match up. Some function could be continuous, but when you take its derivative, it's not continuous, right? And so we don't always know on a piecewise function whether that little point there is going to be included in the derivative or not. Now, in this case, we're going to make sure the function is differentiable. Since we're going to make sure it's differentiable, we know that we have to include it. We want to find the values of a and b that would make this work. Well, just like we might check the limits from the left and the right for a continuity piece, we can do the same process with a derivative. If f is differentiable at 0, then both of those limits from the left and from the right of the derivative are going to have to go toward the same place, right? So that means that from the left, right, the limit of f prime of x as x approaches 0 from the left, well, that's just going to be a, right? And the limit as x approaches 0 from the right of the derivative, if I plug in 0 here, just equals -8. And if this function is differentiable, those have to match up, which means a has to be -8. The problem with this is it didn't just say solve for a, it said solve for a and b both, didn't it? Well, when I took the derivative, I lost that b value, right? So a lot of students get so focused on the differentiable part, they take the derivative, start solving, and either they only get part of the answer, or they end up getting two variables like a and b both. Like how can I solve for a and b? I only have one equation. Well, because there's another piece to this, right? If something is differentiable, we know the limit of the derivative pieces have to be the same from the left and from the right. But don't forget that really important theorem, which we show a lot with mean value theorem and IVT, that if a function is differentiable, that implies that it's also continuous, right? You can't be differentiable without also being continuous at that value. So not only do their derivatives have to go to the same limit, but the function has to be continuous. F has to be continuous, which means the limit as x approaches 0 from the left of just the function f has to also equal the limit as x approaches 0 from the right of f. That's one of the properties of continuity, right? That the left and right limits of the function have to be the same. And so we can also take the limits from the left and right of the original function. Well, luckily for us, we already found out that a was -8. So I can replace that with a -8 if I wanted to. Well, the limit as x approaches 0 from the left of f of x means I'm going to use this top piece in our original function and plug in 0. And all we're going to get is b, because -8 times 0 is going to be 0. And the limit as x approaches 0 from the right of this function, well, we're going to get 4e to the 0 power, or in this case, just 4. So now b has to be 4. So the key here was when something is differentiable, the limit of the derivatives have to match up, but also the limit of the original function has to match up, because if you're differentiable, we know you have to be continuous. Now that statement doesn't work the other way, right? If something's continuous, that doesn't guarantee that it's going to be differentiable. But since we started with differentiable, we were able to work back to that piece of continuity. So let's take another problem here. And again, with the AP exam, I can anticipate, I could see them giving us a function, and then later on in the problem, introducing some more functions. And so that's what we're going to do here in part B. And we're going to see how you roll with this, because I took a problem that a lot of you are used to, and I kind of put a little twist on it, right? Made it just different enough that it might cause you a little bit of confusion because it looks different than all the other problems that maybe you've seen that are similar to this, right? So I want to see how we handle it. So let P be a function such that f of x equals x squared minus the integral from 0 to x of P. Find any non-zero values of x where P has a critical point. So just like we did in the last problem, I want you just to pause for a minute and just think about this problem, right? When you see this problem, first of all, here's what's different. If it doesn't quite feel right to you at first, normally when we introduce a function like P, what we'll say, what you've probably seen is things like P of x equals, x squared minus the integral of f. That's kind of how we typically have, introduced new functions, right? Where here's a new function P, and P equals this kind of equation with f in it. But I kind of flipped it around, didn't I, where P is now part of the integral. So it's just a little bit different than how normal problems have been approached, but yet the math is still going to be the same, which is what the College Board wants to see. They want to see if you can apply things that might look a little bit different, but it's still the same basic idea. So think about this problem and think, how would we jumpstart this problem, right? And I think what's important to realize is we have an equation here, right? And we don't want to get too focused on that because we don't know how we're going to use it. Let's go to the question. Let's go to what they want and think, what are they really asking? Well, they want to know where P, the function P, has a critical point. So if we just think about that for a minute, forget the integral, forget the piecewise function, what does it mean for a function, P in this case, to have a critical point? And just start writing down what these things mean before you start trying to apply the problem and start solving stuff. So if P has a critical point, we know that P prime, its derivative, has to either equal 0 or possibly it could be undefined, right? So a function has a critical point when its derivative is 0 or undefined, assuming that there's a point on the graph, right? There has to be a point. So if I want to talk about P's critical points, the first step is, oh, I've got to find something with P prime in it. I can't find P's critical points unless I have an equation involving P prime. And now that gives you your blueprint. Now we can go back to the information and say, okay, what did they give me? What do I have? How can I create something with P prime in it? I've got to get P prime in the problem. Well, the only thing I have with P in it is this equation. And not only is it not P prime, it's the integral of P. It's almost the opposite of what we want, right? So how can I take this and end up with something with P prime? Well, if you're watching yesterday, we talked about how when you get a function defined by an integral, a really good first step is to just differentiate this. If we differentiate both sides, we get f prime of x over here, and then x squared becomes 2x. And then I'm differentiating this integral, that fundamental theorem of calculus, which is going to be pretty important. And we're going to get just p of x. Hopefully we're getting more and more comfortable with that fundamental theorem. Well, I don't have p prime yet. Remember, but writing this down, it reminds me, I need to get p prime. I don't just need to take a derivative. I have to have p prime. I have to know that specific equation. When does p prime equal 0? So while this was helpful, I still don't have p prime. And the only way to get p prime is maybe take another derivative, right? So now we're going to have f double prime of x, if I differentiate again, equals 2 minus p prime. Hey, now I've got this equation that I'm trying to deal with, right? And I want to know when p prime is 0 or possibly undefined. So I can maybe isolate this p prime, which means p prime in this case is just going to be 2 minus f double prime. It's kind of reversed, just some manipulation there, right? So our p prime equals this, and I want to know when this equation is 0 or undefined. So this is going to be 0 or undefined. That means for that to happen, 2 minus f prime of, or double prime of x has to be 0 or undefined. Well, if we're solving this now I have something I can work with. That means that f double prime of x has to be equal to 2. So if I want to find out when P has a critical point, I need to know when P prime is 0 or undefined. I worked out P prime and realized it was just 2 minus F double prime. So I want to know when that expression is equal to 0 or undefined. So I can just add the F double prime over and ask when F double prime equals 2. And since we're given a nice equation of F, I could pretty quickly take the second derivative. F prime, in this case, is just going to be a, and then the bottom part is going to be negative 8 e to the negative 2x. You'll notice I'm not going to include the 0 because I don't know if it's differentiable. I don't know what a and b are. It might not be differentiable. And then f double prime, the second derivative, well, a is a constant, and so that becomes 0, right? That's our second derivative when x is less than 0. And then the bottom piece, if I take this derivative using chain rule, we're going to end up with 16 e to the negative 2x whenever x is positive. So I want to know when the second derivative is equal to 2. Well, the good news is the top will never equal 2. It's always 0, so that won't give me any solutions where x is negative. The bottom piece, I want to know when this bottom piece equals 0, because that's my f double prime. So we're going to get 16 e to the negative 2x equals 2. And we're going to solve this little algebra problem. Divide by 16, and we get e to the negative 2x equals 1/8. Divide by 16. Maybe take the natural log of both sides, and we're going to get negative 2x equals the natural log of 1/8, right? Using a natural log is the proper algebra way to get rid of an exponential function. And then divide by negative 2, and we're going to get x equals negative 1/2 times the natural log of 1/8. Now this one's going to be kind of interesting because remember, we have this boundary here, don't we, that we have to have this bottom piece only is valid for x values greater than 0. So whenever you get a solution, you have to make sure that that value is actually part of that branch. It's not extraneous. Well, it looks like it's a negative answer because of this negative sign, so maybe it wouldn't work. This is only true if x is positive, but natural log of 1/8 is also a negative answer if you typed it in your calculator. So a negative times a negative, this does end up becoming a positive answer. So this is going to be our x value right here. Now, we have to also consider when f double prime is undefined, right? It's also a possibility. That would only happen in this case at 0, where the two pieces kind of meet. You might have an undefined second derivative there. But notice in the problem, I kind of fixed that by saying there's finding the non-zero value. So we don't have to deal with that 0 part, but it's a possibility you might have to check where those two pieces meet to see if that's an undefined derivative there. So in this case, the only answer is going to be negative 1/2 the natural log of 1/8. And I'm going to turn it over to Tony to finish out a couple more parts of this problem before we wrap up today's lesson.
Yeah, I think what we'll do here is I'm going to move on here to part D, and we'll probably allow you guys to take care of part C and part E on your own. We know a lot of you teachers use our lessons sort of as an extension within your own e-learning. And so part C and E are going to be two fantastic problems that you can kind of work on your own. And then, of course, BC3 and BC4 will invoke these same stems, but ask some slightly different questions. So for part D here, we're going to go back to where your journey through calculus started with the limit. So if the limit as x approaches -1 of f of x over 1 minus x squared is 3, find the values of a and b. So you're going to think about this from the standpoint of, I have a limit here, and we need to take this limit, but by golly, we've got this f of x on top that's just not very specific enough to us. So we can go to this piecewise function, and knowing that our focus here for our x value is around the neighborhood of -1, whether we approach -1 from the left or the right, that's going to lead us to use the top piece of that piecewise defined function. So that f of x is just going to take on the ax plus b value. Now, that's slightly better, I suppose, but we still have this kind of elusive function up there on top that we have to really wrap our head around. And we do know that this limit is going to equal 3. Now, if we think about the process of evaluating limits, one of those protocols says that, well, maybe we could just plug in our value that x is approaching in for x, as long as we have two continuous pieces on the top and the bottom, and we do here. But notice what happens if we do that on the bottom. If we take this limit as x approaches -1, just of this denominator, we find that that gives us 1 minus 1, which is 0. And that kind of makes us scratch our head, and we're thinking, well, wait a minute. How could we end up with something over 0 ever equaling 3? That doesn't seem to make a lot of sense. So hopefully what you see now is that this is a reverse engineered L'Hopital's rule problem. The only way that that limit could be 3 is if we did the same exact process to the numerator, took its limit as x approaches -1, and we have to get 0 for that result. We know that this limit must be 0 in order for this to ever have a possibility of being 3. Okay, well, let's go ahead and take that limit. -1 plugs in for x, and we have negative a plus b that would be equal to 0. And so from that piece of information, from that investigation, we see that the b value and the a value are the same. And that's what our goal is. We want to find out what a and b are. All we know right now is that they are the same. We've established that L'Hopital's rule can certainly be used here. So by L'Hopital's rule, we would just go ahead, dive right back into that limit, but this time take the derivative of the numerator, which in this case is a, take the derivative of that denominator, -2x, and again, we know that that result's going to be a 3. Let's physically replace this x value with -1. You have a over +2 equal to 3, and now it's just a matter of multiplying a 2 over, and you've got your value for a, and you can see that if a is equal to b, you pretty quickly have got your value for b as well. A is 6 and b is 6. I'm a little hesitant to do part E because I really want to make sure that we do it justice, but it's a problem that we certainly want you to take a look at. It's definitely one of Brian and I's favorite questions. It asks you to find the values of both A and B. So it's the same conclusion as the previous question, but now we've thrown in the idea of this second degree Taylor polynomial for a function h of x. H of x is defined to be e of f of x. So that's going to get the juices flowing there when you try to find your values of h of -3, h prime of -3, and potentially maybe h double prime of -3. And you're certainly going to use the facts that those results are 1, -2, and maybe even if you need it, +2, respectively. And from there, you can springboard off into some similar processes that we did earlier in finding a relationship between A and B to get those solutions. But promise yourself, promise us, promise Uncle Brian and Uncle Tony that you'll definitely take a look at part E because it's a really great, great question. But we want to be sensitive of your time. We got a few announcements here at the end, and we want to make sure that we get this wrapped up because some of you have a video I know to watch at 10 o'clock. So Brian, I'll hand this back to you.
Sure.
And
Tony, I think you're going to lead us off with our favorite part of the lesson, our tweets of the day, tweets
our
with Tony.
tweets of the day. Yeah, our tweets of the day. We've got our AP Teachers Rock hashtag, and we're going to give a huge shout out to Andrea Dickey, who has made calculus fun and always celebrates birthdays. Thanks for always being there for me. What a great sentiment by a wonderful student there. And I want to talk about Andrea Dickey is a teacher at Hammond High School in Columbia, Maryland, which actually isn't very far away from where our good friend Ted Gott lives in Galesville, Maryland, who does all of our wonderful work on our keys and keeps Brian and I organized and straight. So congratulations. You do a wonderful job, Andrea Dickey. Your students certainly do care for you. And for our AP Students Rock, thanks to the ABBC students from Bellevue West that have shared their Tuesday time with me to review for the AP exam. And thanks to Brian and Tony and our good friends Virgin Mark over there on the AB channel for all of their time and efforts as well. And that comes in recognition of the teacher who said this was Angie Daughtry. Angie is a teacher at Bellevue West High School, which is in Bellevue, Nebraska, which I believe is outside of Omaha. I want to say outside of Omaha, home of the Thunderbirds, maybe. All right. So there are our AP tweets, and we want to still keep them coming. The well's starting to get dry a little bit. So if you've got a great teacher you want to recognize, if you have some wonderful students, teachers that you want to recognize, send us those tweets.
Absolutely. And don't forget the exam information, May 12th. The College Board's coming out this week with some more information. Last night, they held, Trevor Packer held a webinar for Calc teachers, giving us more information that's going to be pushed out onto AP Central to students. So make sure that you get a hold of those videos. Really good informative stuff about how you're going to upload your tests, how the platform is going to work. Just really good information. There's always videos for each piece of these. So we'll be focusing a lot of this next week. We're going to have a lot of practice on the actual testing component of it. That way there's no anxiety about what's going to happen on test day. So that'll be happening a lot next week in our sessions, but you can find good information on the College Board as well. Tomorrow, we're going to talk about verbal interpretations, explanations, and reasoning, any good calc exam is going to want to get your thoughts. They want to hear what you think, not just the math that you do. And so just like any exam, you're probably going to have to give some interpretations of your answers. Here's my number. What does this mean, right? How do I explain my reasoning? What's the proper way to justify answers when they say explain or justify? What are they looking for, right? So we're going to really hit that tomorrow, and then Friday, putting everything together, some good connections of all the things from this week, tables, graphs, algebra, explanations, piecing it together to really give us some good experience of kind of comprehensive problems. So with that, our pets of the day, keep sending your pets, keep tweeting out. Teachers, tweet out about your students. Students, tweet out about your teacher so we can make sure that we celebrate you guys, and keep tweeting your pets on getting some cool pets. We have Molly Weasley from Evie, and I had to include Molly Weasley, Tony, not just because of the Harry Potter reference, I'm assuming, but last week Evie made a Twitter account just to hop on Twitter and tell us that she's been watching our videos every day. So she made a Twitter account just to tell us that. And her avatar for Twitter is my favorite #1 mathematician, Gauss. So I can't tell if she was sucking up or she likes Gauss or not. And she even mentioned it's Molly Weasley's birthday today. So I can't tell if that's all just an effort to get her dog, but anybody with that effort deserves to have their pet featured regardless. Then we have Levi and Luis from our friend Amy, 2 beautiful dogs. And then the dog Rookie here from Steve. There's another picture he shared where the dog is like catching a Frisbee, but he looks pretty ferocious. So I thought I'd just give this picture right here. And then of course, what would be pet of the day without Squirtle the tortoise from our good friend Benjamin, and a nice little Pokemon reference there. So there's your pets of the day. Keep tweeting us out. Join us tomorrow and Friday as we continue this, getting you ready for the BC exam. And then don't forget, next week, we're going to be giving lots of practice problems and giving you a chance to even upload your answers into the system. We're going to try all of that live on these AP Calc BC live sessions. Tony, final thoughts today.
We just want you to continue working hard. You know, we've said it many times, we believe in you. We just want to make sure that you believe in yourself. We still have several days to work together, and we have this common goal, and that's for you to rock this AP Calculus BC exam, and it's going to happen, right?
Absolutely.
Stay safe. Keep learning, you guys.
Yep. And tune in tomorrow to figure out how close we can come to that 10 a.m. ending time, while we continue to give our producer Sarah a heart attack on the back end, wondering, are we ever going to finish these lessons? So see you guys in the morning.
Bye, guys.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes,